Hello, peer reviewer. My name is Elizabeth Williamson, and this is Lab 3, Black Hole. This lab follows a star orbiting a black hole of initial unknown mass, where code is edited and analyzed to estimate the mass of the black hole. In this lab, we will again start by exploring Newton's second law. In order to find the net force, we use the derivative of momentum over the derivative of time, or the change in momentum over the change in time. Here, momentum is still mass times velocity, where the mass of the star is 2 times 10 to the 30 kilograms, and the change in mass as well as the change in velocity are final minus initial. Net force is also further explored in this lab through the parallel and perpendicular forces. This is so that we can see the forces that determine the direction of the star as it moves around the black hole, which is the perpendicular force, and the speed of the star as it speeds up and slows down due to the parallel force. In this lab, we found parallel force through the formula d magnitude p over dt times p hat, with p hat equaling p initial over the magnitude of p initial, and d magnitude p over dt equaling the change in the magnitude of momentum over the change in time. With parallel force, we can find perpendicular force with a variation of the net force formula at the top of the page by moving net force over to the same side as parallel force and then solving for the perpendicular. With all of these elements, we can now find the mass of the black hole through a variation of the gravitational force formula, where the mass of the black hole equals net force times the radius squared over the gravitational constant times the mass of the star. Here are all of the aforementioned formulas input into the code, along with the gravitational constant, star's mass, and the time of one rotation around the black hole, which is 1 day, or 86.4 thousand seconds. This is the video of the simulated star moving around the black hole. Here we can see how net force, which is equal to 1.012 times 10 to the 29, is always pointing towards the black hole due to the vector addition. We can also see parallel, which equals 1.53 times 10 to the 28, and perpendicular force, which equals 1.002 times 10 to the 29, in action, and how the parallel force increases in the direction of the star's momentum as it speeds up, and then decreases in the opposite direction of the star's momentum as it slows down. This also relates to the perpendicular force determining the rotation and direction of the star around the black hole, which then determines how far away the star is from the black hole during orbit and, in turn, how fast the star is moving due to the black hole's gravitational force. But what does it mean in terms of how rate of change of momentum is different from the net force? The net force and all of its components are different from the rate of change of momentum and its components due to the fact that without the parallel and perpendicular forces that make up the net external force, you cannot have all of the change in momentum due to their cause and effect relationship. Here we can also see the mass of the black hole changing based upon where the star is in its orbit. The change of the mass is due to the net force and radius changing during orbit, which affects the numerical input in the equation that solves for the black hole's mass. These numbers can then be averaged out to find the estimate mass of the black hole, which turned out to be 1.896 times 10 to the 34. Now, what if the current black hole was removed and replaced with a different black hole in the same location? Would it be possible to find a mass for the new black hole? The answer to this is yes, simply because the motion of the observed star remains the same. This means that all of the points that determined the mass of the original black hole are still the same, so the mass of the new black hole would be easily solved for with the same methodology as seen in this lab. Thanks!